You have all the information on the website, funglass.org, and you will have still 3 sessions in the 3 next weeks about the glass and related to the project topic. Thank you very much. Thanks.
Okay, so when you are ready, please tell us. Okay?
We are ready. That's okay. You have the floor.
Okay, so good afternoon to everybody. This is as Vanessa mentioned, the second session of the Funglass Days here in Aveiro, Portugal. Our section is about solid-state lighting. We have 3 different talks. The first one, you can see the title on the screen, Sol Gel Derived Organic and Inorganic Hybrids for Lighting. And the talk will be presented by Professor Ruth Ferreira, which is professor here in the Department of Physics of the University of Aveiro, Portugal, and also Vice Director of our Aveiro Institute of Materials. So, Ruth, please, it's a pleasure for us having you here talking on the Funglass Days.
Okay, thank you very much. And also thank you very much to Funglass to this invitation to be here in Funglass Days. And welcome to my presentation where I will illustrate how sol gel derived materials has been used here in Aveiro to address some of the main challenges in the field of lighting. Okay, conventional lighting was supported in the past by extremely inefficient lamps. For example, only 5% of the energy consumed by an incandescent lamp was converted into light, and this value was a little bit higher even for compact fluorescent lamps. And this value accounts for 90% of the worldwide energy consumption. So the solid-state light is an area where growth and emerging technology with the ability to convert light into electricity more efficiently than that observed in conventional light sources, enhancing the reduction of energy cost. And this is essentially because of 4 main features: long lifetime of LEDs, low toxicity, cold radiation, and up to 80% of energy saving. In fact, LEDs are the 4th generation of light sources. Generation 1, lamp gas. Generation 2, the old incandescent lamp. Generation 3, the fluorescent lamp. And now Generation 4, the light emitting diode in 1996. And this was in fact boosted by the blue LED invention in 1993. The technological and societal relevance of LEDs was in fact recognized in 2014 by the Swedish Academy that attributed the Nobel Physics Prize to the invention of LEDs emitting blue light, mentioning that they are precursors of saving energy sources. So we may say that the appearance of the blue LED was the key to the replacement of incandescent and fluorescent lamps towards a more sustainable lighting. Nowadays, we can identify 3 main principal methods to generate white light with an LED. A blue LED chip covered with a yellow phosphor, a UV LED joined with red, green, and blue phosphors, or the individual assembled in a single device of the red, green, and blue LEDs. So the first generation of white LEDs was based on a helium gallium nitride chips emitting blue around 460 nanometers that were combined with cerium YAG phosphor. The second generation is still based on a blue emitting LED, but combined with a mixture of orange and green inorganic phosphors. This first generation, and it's just by curiosity, is a photograph of the current white LED, where you can see the emissive layer, the blue emitting layer that is coated or covered with the cerium phosphor. And also just for you to note a little bit about the chemical content of the LED, you can see an elemental mapping of some of other elements also present in the current LED. So the question is, what are in fact the disadvantages of the current white light? On one hand, the blue LED varies slightly between units. The ratio of blue and yellow light is variable, and white light has a lower amount of red. So the white light has different characteristics. And although LEDs are present on a massive scale in various areas, challenge remains. To understand better the challenge in the field, we need to understand how to compare the white light from different sources. There are two main figures of merit. One is the correlated color temperature, CCT, which is the temperature of black body radiator that emits the same color of the light source. In general, CCT values range from 2,500 to 6,600 Kelvin. For instance, a candle has a CCT of 2,000 Kelvin and incandescent lamp 3,000 Kelvin, a little bit higher for a fluorescent tube, and LEDs, CCT typically varies between 4,000 to 8,000 Kelvin. Low CCT values usually correspond to warm light, whereas high CCT values are attributed to the so-called cold light. Comparing to natural light, high CCT values typically mimic a sunny day with a clear sky. And this can be achieved with fluorescent lamps and LEDs. For instance, if we think about sunlight, we have noon sunlight, we have a lower CCT that can be mimicked by fluorescent lamps. And if we go further in the day, 1 hour after the sunrise, or even at the sunrise and sunset, very low CCT values correspond to the natural daylight. And I call your attention that sunrise and sunset can only be mimicked with a candle. So how is this managed in artificial light? White light with different values of CCT in fact results from the balance between the amount of blue, cold light, and yellow, warm light. Here I show to you some LEDs with a low CCT value, in which we have a larger portion of yellow phosphor emission compared to the blue one. If we increase the CCT by increasing the relative amount of blue with respect to the yellow, we can see that there is an increase in the CCT. And finally, if the blue color dominates, the CCT increases the correspondent value. And I think that those three photos here of this LED strip show very well the difference of the white light arising with the different CCT values. So it is known that cold light with a large contribution of blue is beneficial during the day for short-term exposure because it promotes the increasing of attention and the reaction time, but it is also known that it may be harmful at night. In particular, it alters the circadian rhythm and may affect vision. Here is just a curious example. It was an art project in Amsterdam where the lights were illuminated with blue light. And under this situation, under the illumination with blue light, the human eyes loses the ability to view the details. And in fact, there were some traffic accidents during this project. So this project is no longer running as far as I know. Okay, I mentioned that we need at least two figures of merit. In addition to CCT, we also need to evaluate the color render index that in fact is strictly related with lighting effect on color perception. We may understand CRI as a quantitative measure of the ability of a light source to faithfully produce the color of an object in comparison with a black body light source. Typically is a number between 0 and 100, meaning that if a CRI is 100, the color perception of the object under artificial light will look exactly as if you are using natural light. So let's see how to choose a CRI depending on the application. Typically, reduced values below 600 can be found, below 60 can be found in high pressure mercury or sodium vapor lamps. You can find them in outdoor illuminations, roads and streets. A medium CRI can be found in fluorescent lamps and LEDs and is applied in outdoors illumination or space occupied for a short time. A good CRI between 80 and 90, you can only be found intrinsically in fluorescent lamps. It is ideal for interior light, schools and sport activities. And finally, the excellent classification for CRI above 90 can be found in incandescent lamps, and it is ideal for interior light, shops and museums. In this slide here, I would like to show some examples that illustrate the effect of the CRI on color perception. You can clearly see that as the CRI increases, it reveals bright colors, which is particularly evident in these red objects over here. So we may say that applications in the field of solid state lighting requires the development of new light emitting materials that combine benefits for health, warm CCT, high color render index with materials processing, easy recycling, absence of critical elements, and reproducibility. So let's focus a little bit on the benefits for health. The design of smart light sources that mimic natural daylight with direct application in the control of circadian rhythm, human, animals, and plants is desirable. Here, this slide illustrates some events that make part of the human circadian rhythm that lasts 24 hours, as all of you know very well. I would like to highlight here two aspects: the melatonin secretion that starts in the beginning of the night and that stops in the beginning of the morning. And why melatonin? Because this is a hormone that participates in the temporal organization of the biological rhythm. It mediates the transition between day and night cycles and also regulates several physiological processes. And here I show to you that how CCT is strictly related with the suppression of melatonin. High CRI values may lead to a suppression of melatonin of the order of 80%, where, for instance, under candlelight illumination, the suppression will be only 2%. And the relevance of the control of the circadian rhythm is well illustrated in this example. For the first time, there is a report on the influence of a circadian rhythm in a plane crash by the China Airlines in 1985. The National Transportation Safety Board clearly expressed that the factors that contributed to the accident were captain failure to adequately monitor the aircraft flight management due to a failure of the circadian functions. Other examples typically occur in workplaces where activity continues around the clock. Skill-based errors exhibit a significant circadian rhythm dependence, being most prevalent in the early hours of the morning. And like animals, also plants have a circadian rhythm at 24 hours synchronized with the day-night cycle. So LEDs lighting in agriculture and horticulture have, of course, the motivation of growing faster, better, and cheaper. The idea is to meet the demand for fresh food in any time of the year at affordable prices. And if we compare the LEDs versus conventional illumination, we find out that LEDs generate the same harvest yield using only 25% of the energy. LEDs produce much less heat, as I already mentioned. This means that the LEDs can be placed very close to the plants, including the lower branches and lower sheets, without the danger of burning. This means that we will favor photosynthesis. And this is also an example that I found very interesting, because there are plants whose growth is slower at night than during the day. For instance, pumpkins are an example where the evening growth is under control of the biological clock. Photosynthetic products are used during the night to assist in the cellular uptake of water by increasing the turgor pressure and cell growth. So the question is, what will be the generation 5? What are the new LEDs? Of course, we should look for sustainable processes. We need to control the circadian rhythm of humans and plants, and it is required improved optical properties. As I mentioned, high CRI, low CCT, and also address the question of the green gap that I will explain in a moment. And this is certainly a window of opportunity for sol gel derived materials. So the question of the green gap issue appears due to the lack of efficient mini-emitting semiconductors. This figure here, this graph, shows the external quantum efficiency as function of the wavelength, and we can clearly see a drop and the efficiency in the green spectral region. So in parallel with the need to develop white light emitting sources, there is also a need to develop green emitting materials for solid state lighting. And here I bridge directly with the examples that I want to show to you. There is in fact a window of opportunity for sol gel materials such as silicates. And why sol gel silicates basic phosphors? Because they are characterized by low phonon frequency, high thermal stability, which mean that we can incorporate a large amount of lanthanide ions that yield efficient phosphors with the ability to convert deep ultraviolet and near ultraviolet light into the visible. These silicates typically are incorporated into polymeric or silicon resins. Why? Because we need, of course, to process them as films so that we can develop a prototype. And today I select two examples to show to you. One is the case of a barium silicate that was incorporated into a PMMA film, polymethyl methacrylate film, that was used to coat a bare UV sheet emitting at 365 nanometers. Here, this photo illustrates a prototype and the bright resulting green light arising from the high quantum yield of the phosphor that is around 50%. The prototype emission was studied as a function of the ultraviolet sheet operating conditions, revealing a minor color variation in the green. The luminous efficacy, in this case around 7.2 lumens per watt, is one of the best values in the literature for this kind of materials. The other example that I select for today is also based on European 2+, but incorporating into the so-called S2S silicate. And this time what we want is to generate white light with controlled CRI and CCD. So this silicate was combined with a commercial aluminum oxide in distinct rates. Again, it was processed as a film through the incorporation in polymethyl methacrylate. It was deposited on the top of a bare LED, this time with a higher excitation energy, 395. And as I will show to you, we are going to use different ratios between the commercial oxide and our S2S silicate. The commercial oxide reveals a blue color, whereas the S2S silicate displays a yellow color. By varying the ratio between them, between 20 and 80%, it is possible to tune the emission properties. Here you can see that we can tune the emission from the blue to the yellow spectral range, crossing the very important white region that is the center of the diagram. If you look into greater detail to the emission spectrum of those prototypes, you can clearly identify that the contribution of the commercial oxide, the relative contribution can be tuned, and therefore we can control the properties. If you want to quantify them with the figures of merit that I have been mentioned during this presentation, you can see that the CCT can be tuned from very low values around 3,000 up to 8,000, and also the CRI can be increased from 58 up to 84. Very interesting is also the luminous efficacy that, as I mentioned, in this kind of materials is typically of that order. In this case, the maximum value that we end up was 8.5 lumens per watt. Okay, this is one class of materials that were typically incorporated into polymers, but we want to address today, or I want also to address today, sol gel derived organic and inorganic hybrids. And why? In fact, the first examples of the use of hybrid materials in solid state light comprise layered crystalline organic and inorganic perovskites. In fact, at the time, it was reported a maximum efficiency of 0.16 lumens per watt, a value one order of magnitude than I just reported before. But in any case, those first examples reveal white light color coordinates with quite interesting values for CCT above 6,500 Kelvin and very high color rendering index above 85. After those initial works, the research in the field has been driven by the development of diverse organic and inorganic hybrids with a huge potential for lighting technologies. Here I will highlight 3 examples: in situ sol-gel derived terbium-based hybrids, carbon dots and European complex modified hybrids, and finally I will address the case of oxide-based hybrid nanoparticles. So what are the organic and inorganic hybrids that serve as a host for the emitting centers? We select typically the diuresyls and triuresyls. Typically, they are made of polyether chains of variable length. They can be in a linear or in a branched structure that are covalently bound to a siliceous backbone through urea groups. The selected hosts, and this the rationale for the selection of these hosts is that we have been demonstrating along the times that besides the possibility to processing the final materials in the form of thin films in virtually any substrate, they provide increased mechanical and thermal stability, and they also increase emission efficiency and photo stability. One of the known problems associated with incorporation of optical centers into hybrid or polymeric matrix is typically the low solubility of some of the complexes. Thus, to mitigate this issue, we use in situ synthesis, which was exactly the case that I'm showing to you in this slide. This is the case of a salicylic-based terbium coordination polymer that is not soluble in the diuresyl precursor. Thanks to the interaction between the diuresyl and the complex synthesized in situ, we obtain a green luminescent material with a quantum yield up to 40%. So the hybrids are typically processed as freestanding films. Here you can clearly see that the final films are transparent, and under UV radiation, you can see the bright green color. And why we have those properties? Here I have the excitation spectrum that nearly overlaps the absorption one. So we can clearly see that these materials absorb essentially the ultraviolet, meaning that, okay, they can be potentially used to be excited with an UV LED, and then the emission and the excitation in the ultraviolet displayed the very well-known F8 transitions of the terbium. So this material was used to coat a commercial ultraviolet chip. In fact, it was one emitting at 365. These are real photos of our prototype. You can clearly see that the film was deposited over the interior where the electroluminescent LED appears. And finally, just to give you some figure of merit for us to have one idea about the performance of this prototype, here we have a luminous efficacy up to 21.5 lumens per watt. Okay, featuring now again white light based on organic and inorganic hybrids, we decide to replace the terbium complex by an European one. And the idea was to provide the red component for the white light. The green and blue components were in fact provided by carbon dots that display a broad emission in the blue-green spectral regions. The rationale for the use of carbon dots is based on their low cost. They are sustainable materials from abundant resources. Their incorporation into the diuresyls enables the preparation of transparent and flexible films. Once again, we deposit our material on the top of a commercial LED chip, this time emitting in the blue. And to be able to tune the CCT and the CRI of our prototypes, this time we decide to keep exactly the same concentrations of the European and of the carbon dots, but we decide to vary the thickness of the layer deposit on the top of the bare UV sheet. This means that the relative contribution, and you can clearly see here in the emission spectrum that the thicker the prototype or the thicker the layer of the hybrid, of course, the lower contribution from the LED chips. And because of that, we were able to fabricate prototypes with tunable CCT from cold to warm white light with CRA values quite interesting, up to 89. So the last example that I would like to show to you today is the case of oxide-based hybrid nanoparticles that were also prepared by the sol-gel non-aqueous routes. This time we decided to use two metal alkoxides, aluminum and zirconium, plus benzyl alcohol. So the benzoate nanoparticles are in fact platelet-like nanoparticles. They have a crystalline size of 4 and 13 nanometers. Whereas the benzoate capped zirconium nanoparticles are highly crystalline and uniform and have an average size between 3 and 4 nanometers. If we focus on the emissions, on the photoluminescence properties, we can see in the excitation spectra of both nanoparticles the contribution of the excited states of the benzoate groups. And for the case of the boehmite nanoparticles, we can see also the contribution of a defect that is very well known in the literature, is the so-called F-center defect. Whereas in the case of zirconia, we have an oxygen-related defect that is responsible for an absorption in the high energy side with lower UV spectral range. In what concerns the emission, we have a broadband emission in both cases. For the boehmite nanoparticles, the emission is a combination of the benzoate triplet state and of the F-center defect. And of course, in the case of the benzoate zirconia, we have also the contribution of the benzoate excited state, and some oxygen-related effects are also contributing to the emission. And the very intriguing aspect is that the quantum yield is really different despite all the similarities that I have been shown. Whereas the quantum yield for the boehmite nanoparticles is 58%, for the zirconium-based ones, we end up with a maximum value of 4%. In a very simplified way, we can understand the reason. I have to say that this was model, and you can find the calculations in the literature. And here I will explain to you the main concept in a qualitative point of view. Okay, both nanoparticles have, of course, the contribution of the triplet and singlet excited states for the absorption and emission features. And in the case of the boehmite, we must add the excited states of the F-center. And in the case of zirconia-based nanoparticles, we need only to add the singlet state related with the zirconia oxide defect. And you can clearly see here that there is a resonance, an energy resonance between the triplet state of boehmite and the triplet state of the benzoate. And in fact, this is the so-called triplet sensitization that in this particular case yield to a very large quantum yield. So of course, having those two nanoparticles with such a distinct quantum yield, we select the benzoate capped boehmite nanoparticles to produce a prototype, of course. So B1, B2, and B3 are 3 prototypes that we developed just changing the calcination time of nanoparticles. You can see that in all the cases, we end up with white light. And here I show to you the prototype that was developed here. You can see very well the white light coming from our LED. Very interesting is that if we compare the helium gallium arsenide nitride LED that we are using in the excitation, plus the emission of the boehmite nanoparticles with that of the commercial LED, we find in fact some similarities and some differences. And the main difference is that our spectrum is broader. And this is the reason why we end up with best performance numbers. In fact, our device shows a higher CRE value, 86, compared with that of the Axiom, 79, due to the broader emission spectrum. And another important aspect is that since we are using a single white light emitter, not the combination of blue and green, blue and yellow color, this means that emission spectra are independent of the forward current, presenting therefore no color shift under distinct work conditions. So our optimized device displayed a CRI of 86 and a CCT value of 6,000 Kelvin. So concluding, and I have to say here that, of course, I focus today on some prototypes, but of course, there is a systematic work, and this is only the result of some of the optimized samples. Typically, what we do is basic and applied research on soil gel-derived organic and inorganic hydrates for lighting. Here, I reported to you lanthanide ions incorporated into silicates and ureazyls and benzoate hybrid nanoparticles. Typically, the samples are characterized from the structural, morphological, and optical point of view so that we are able to feed back to the synthesis. And this input allows us to determine the performance that again will feed back to the characterization and to the synthesis conditions. And in all the cases, those prototypes, we were able to, in certain way, model or interpret the results and try to determine the reason why those samples display a best performance or a better performance. So I'd like to thank you for your attention and of course the funding agencies. Thank you very much.
So the time is open for questions. If someone wants to put some questions to Ruth. No, I'm checking. Lionel, are you listening to us?
Yes.
Okay,
yes.
So maybe you can start with I know that you have some words to the community. So
Yes. Thank you, Luis. Thank you, Ruth, for the talk. Thank you for this very nice talk. I'm really sorry to apologize because we have some delay just to start the Zoom session. In fact, some of you were connected to another session. Well, an old session, the previous session. So that's why we have a little bug between the two. But I think now everything is all right. So good afternoon to all of you. And well, I'm very happy to say this word of introduction. I'm a little bit late for this, but okay. This is in the series of conference, which is in the framework of the International Year of Glass. Each time, Year of Glass and Year of Light, but light and glass are very entangled. So let's say that it's Year of Glass, which is very nice also. And well, we organized this conference in the framework of the international project, which is FunGlass, which is a RISE project, an European project. And we call them FunGlass Days, okay? Because our project is really targeted to fun glass. So we try to make some fun with glass and a lot of applications, and you can see those applications today, which are dedicated to photonics material for lighting. So we have scheduled every Tuesday afternoon those different topics in 5 universities, and we try to present technological advances in the field of glass science linked to photonic applications. Each university tries to host a thematic discussion from the viewpoint of academic researchers, but also from companies, which is very important to my point of view. And this is also an opportunity for all of you, well, to think about new horizon, because let's say that those conferences are very broad, and you can have some new idea about your research development, but maybe also for future products or collaboration. So this is nice. And for the young researcher, this is also a way to access for companies, leading companies, roadmap, and maybe a job market if they are looking for a job after their PhD or whatever. So I just want to say that I think Vanessa just explained that we are recording this and streaming this meeting in the channel, which is a FunGlass project. You can see on the YouTube. And okay, so now we can go for the next talk, and thank you again.
Okay, Lionel, thank you. So I think that we can move now for the second part of this section. This second part is devoted to people from companies. Okay, we have the pleasure to receive here three previous students from the group that are now working on different companies. And then I will start with the first presentation that will be made by Vânia Freitas. I asked Vânia to try to share her screen, please.
I can't because I'm not.
Okay. So
I don't have a permission.
Okay, thank you, Vânia. So, Lionel, can you please give permission to Vânia Freitas to share her screen? Okay. Vânia, can you do this now?
No, not yet. It's okay, no.
Okay. Okay, so before, let me say some words about Vânia. Vânia Teixeira is a biomedical engineering, and then has a master in micro and nanotechnologies from the University of Minho in Portugal. After that, she received a PhD in physics in a joint agreement between Aveiro University and Montpellier University. And since 2017, she works in a company near Aveiro, and that company is a lighting industry, but I think that Vânia will talk much better on this subject than me. So please, Vânia, you can start, and I should say that it's for me or for us a great pleasure to receive you here. Okay, so go ahead, please.
Thank you, Professor, for the invitation. Today I'm here to speak a little bit about the light engine company and the projects that we are developing in Portugal and in Agda. So light engine, okay. Sorry, this doesn't work. Okay. Light Engine is a company that makes part of a group of 5 other companies that dedicate to the electronic development. For example, Peak Advance and Globaltronic are the companies that dedicate to electronic development. HFA and Wartronic do the production of the electronic developed by Globaltronic and PIC Advance. And after we have Light Engine that I'm representing here and Lightmobile. Light Engine is a lighting company, and Lightmobile is dedicated to mobility of cities, basically in bike sharing. This doesn't work really well, okay. Light Engine is a company with 16 years, and it was founded in 2006. Start with the project, Luminotechnic project for another companies. In 2010, start the developing of products, lighting products. After 4 years, start to the industrialization of lighting products, and in 2016 start to the process of certification of the company based on ISO 9001, the quality certification. The certification of the company was accepted in 2017, and in the same year we started the certification of the company based on research and development products that it was certified in 2019. The company it's growing, and now we have around 4,050 meters square of area for production, and has you can see in the graph we are growing in terms of invoicing, and at the moment we have we can have our products in different countries, Portugal, Spain, Belgium, Germany, Emirates, Qatar, and Oman. So we are a lighting company that ensure the design, the efficiency, and we integrate control systems in our luminaires. We develop lighting products for different areas, hotel, hospitals, office, industry, public lighting, and we are leaders in the market, in retail market. In addition, the light can be used in different domains, as Professor Hood speak a little bit before, in human-centric lighting and horticulture. Light Engine have also products in these domains, in smart cities, health and well-being, horticulture, lighting and acoustic, light quality, and also inactivation of the virus and bacteria. So, light, both natural and artificial, plays a crucial role in the creation of a sustainability built environment and democratic architecture with the people in focus. Some decades ago, most of people were working outside. Nowadays, the number of people working inside of the buildings are really high compared with the ones that are working outside. So 19% of people in the world works in biological darkness condition, and we have a problem with this. The indoor lighting allows to see, however, doesn't allow the stimulation of our body and brain. And this is affect us in terms of our body, physically and psychologically, and has a direct impact on our health and well-being. If we compare the luminance on a sunny day, we can have around 1,000 lux. When we compare with a cloudy day, we can decrease 10 times of number of lux when compared with a sunny day. If we go to indoor office or a school, the lux can decrease 200 times compared with a sunny day. This is critical for our body and our well-being. So, in terms of looks, we can stimulate our vision with around 50 to 500 looks. But our body and the non-visual stimulations just can be stimulated with a value of looks below to above to 1,000 looks. And this is really important nowadays because almost of people are working in the dark conditions. So in Light Engine, we are using a technology developed by Nisha that changes the typical spectrum of light, where they increase the cyan components, they decrease the yellow components, and they enlarge the spectrum in order to increase our vitality and decrease our tiredness. Change a little bit the topical, but speaking about the light, we are developing multifunctional systems for office because the many successful spaces have a common problem: the poor acoustic. The Wall Street Journal recently cited a study that found that once distracted, it can take the average work 23 minutes to regain concentration on a task. So it is important to develop systems and products in order to provide the best conditions for the people that working on the office. During the last 2 years, we developed 4 main products, and at the moment we are working in a new project with the University of Aveiro, where we want to develop products that can integrate light, acoustic, and odor absorption in order to have the vision, the acoustic, and the smell in the best conditions for working. Here's a roadmap for improving the quality of our air, water, and light, with the inspired design decisions that not only keeps us connected, but facilitate a good night's sleep, support our mental health, and help us do our best work every day. So in this way, 86% of property managers and analysts expect to increase their investment in the well-being in the next 3 years. This topic is really important for the office and for the well-being of the people on the work. Another topic that we are working on in Light Engine is the horticulture. Since 2019, we develop electronic in Globaltronic, and we have the production in HFA, and we do the integration of the PCB models in light engine basing
Sorry,
on...
Vania. Sorry, I think that there is a problem with your presentation, because
Why?
now we are not able to see. Can you share it again?
Yeah, of course. And now?
Ah, okay, okay.
It's okay?
Yes.
So,
Okay.
it's okay?
Yeah.
Okay.
No, it's okay.
I don't know if it's better.
No, you
no,
can.
it's okay. Okay. So, in the topic of horticulture, we, since 2019, we developed two different luminaires where we integrated two different PCBs with the control, and where we integrate 5 types of LEDs with different colors and can be controlled based on the conditions that we want to expose the plants, the vegetables, the fruits. We develop a top lighting, for example, and we can use in cannabis with the distance between the plant and the light. It's more or less 2 watts. It's a high power luminaire that integrate PCBs with 5 channels that can be changing in terms of ratio the colors. And depending of the stage of growing the plants, we can activate different channel with the time. The interlighting and vertical farming, it's used for small distance, around 50 centimeters, and can use it, for example, in cucumber and tomato. This one, we don't have a control, and we also integrate 4 different LED with the different wavelength. The last topic that I want to speak a little bit is emerging in 2020 with the COVID. And it was a project that we developed with the University of Coimbra and also Globaltronic. Here we integrate different UV radiation in order to check UVA, UVB, and UVC, which one have more successful in the inactivation of virus and bacteria, different virus and bacteria. And UVA and UVC were the more efficiency, depending, of course, the time and the price. We can integrate in Rubish, that is a robot that we developed in this project, and can inactivate virus and bacteria. This robot is autonomous and can go through, for example, in the hospital and inactivate on the surface virus and bacteria. So, thank you very much, Professor, for the invitation. I hope that this presentation of the work that we are developing in light engine motivate the development of new LEDs and new solutions in order to be integrated in the future projects in light engine.
Okay, so Vania, thank you. Thank you very much for your presentation. So I ask if there is someone that wants to pose some questions or comments. Okay, so if not, I pass to the next presentation, okay, which is also will be an in-person presentation. In fact, two-person presentation. It's my pleasure also to receive here again in Aveiro Ana Rita Bastos and Ana Rita Frias. Okay, I'm pleased. So they are former PhD students of the University of Aveiro, one in telecommunications and another one in physics. And now both work in a company, also nearby Aveiro. The name of the company is CMOL. They will speak, of course, about the company. Now, I'd like to say once more that it's a great pleasure to see that previous students of the university and of the group now are working on companies, flying with new wings. Okay, and this is very important. Okay, thank you.
Thank you very much. Hello, everyone. My name is Ana Rita Frias.
And my name is Ana Rita Bastos.
And first of all, thank you very much for the invitation to be here and to share our professional experiences, having in mind that we belong to this group since 2 or 3 years ago. And we are here representing the Research and Innovation Department of Simulch Plastics. Starting with my background, as Professor said, I did here at University of Aveiro my PhD in physics in luminescent solar concentrators. After that, I did a short postdoc at the Instituto de Telecomunicações and readily jumped to my first industrial experience at Castro's Iluminações. There I worked as an R&D engineer and developed light embedded products for the construction industry. After that, I came to Simulch, where I started as a R&D project manager, and nowadays I'm the lighting unit manager. Besides my responsibilities at leading this team, I'm also the optical engineer, where I perform some optical design and simulations for light guides, having in mind that we are trying to develop ambient lighting for the automotive industry.
So now about my background. I did my master degrees in physics engineering with Rita at the same time. Then I passed to my PhD in telecommunications, namely in photonic integrated circuits with organic and inorganic hybrids for optical communications and sensing. Then I did a postdoc at CISEC Institute of Materials in the Phantom G group, led by Professor Luís Carlos and Professor Ruto Ferreira, where I work in two main fields, the nanothermometry and also sustainable luminescent solar concentrators for smart windows. And I had a researcher position at the Telecommunication Institute in the Optical Quantum Communications Group, where I managed two of the research projects there and working the projects that were concluded with two field prototypes in a quantum network. And then I had the opportunity to go to the industry, so Simulch Group, the plastic division, invited me to go there as an R&D researcher. So now I am as an electronic engineering in the lighting unit, where I develop hardware, design hardware with a colleague of us. And I'm focused more in the software solutions, development of embedded software for ambient lighting in the automotive industry for Simulch to start this new business in-house.
So, Simoldes Plastics is a Portuguese company with over 40 years of experience in the injection of plastic parts for the automotive market. Simoldes Plastics is part of the Simoldes group that is divided in two main divisions, the tool division and the plastic division. The tool division has 1,000 employees and is one of the European leaders of tool injection for plastic parts for the automotive market. The Simoldes Plastics is the company that injects uses the molds for the plastic parts injection, and our main customers include Stellantis, that is the former PSA group, VW, Skoda, Seat, Opel, Porsche, among others. The mission statement of Simoldes Plastics is to be the preferred choice of our customers, employees, and suppliers, contributing to a sustainable growth and satisfying our stakeholders with values that are deliver our commitments and trust on each other. As you can see, both Simoldes Tools and Simoldes Plastics have a huge number of companies in Portugal and around the globe, as you'll see. Our worldwide presence regarding the plastic division, we are present in 8 countries, starting from Portugal, Spain, France, Germany, Czech Republic, Poland, Morocco, and Brazil, with 9 plants, with over 402,000 employees. Simoldes is growing in all of the regions, starting in Portugal, where we have our headquarters and the technical center. We also have 3 production plants. In France, Morocco, and Czech Republic, we also have 1 production plant. In Poland, nowadays, we actually have 2 production plants, and as well as in Brazil.
So the big extensive portfolio of Simoldes is mainly focused on the automotive industry. So Simoldes Plastics produce plastic parts for the interior and the exterior parts of the car. For the interior part of the car, we developed trims, the upper and lower ones. In the roof, several components, the cover, mirror, and the storage. Also, the doors are several components of the doors, and also the door panels, which is the core business of Simoldes Plastics, is to produce these door panels. We are now producing door panels for Stellantis and Volkswagen Group, Seat, and so on. And we also have the assembly lines for these door panels, where we assemble every part, the plastic parts, the clips, and also electronic units and harness that are needed. We also develop for seats, for handles, and so on, for the cockpit, the glove compartment, the dashboard, and the central console. In the exterior of the car, we have for all of the sides, the back, the front, and the lateral side of the car, the trim in the front of the car, and also the cover of the engine, and now for the electric cars, the cover of the batteries. Besides the automotive, Simoldes Plastics also have some products non-automotive. These are mainly produced here in Portugal, in Plastaz. So we produce supermarket cars with big injection machines and molds. We also develop the plastic parts for baby chairs, namely for we do 100% of the shares of Bebé Comfort Company. And we also have an assembly line to have these chairs. We also have the bottle covers for Galp. We cannot see here, but this for Pluma. In this case, the production is a little bit different because we have the plastic injection, but also in mold labeling. In this case, while we are injecting the plastic, we are putting a label in the plastic part to have the Pluma logo. And we also have the grids for glass bottles for Superboc and Coca-Cola and so on. Of course, to produce all of this, we are a big company with a lot of skills, not only to produce in the serial production, but also before having this production, we need a lot of engineering skills to manufacture and injection molding for the plants. We need these skills, but also in the engineering department, we have a lot of CAD designers to design all of the pieces in 3D, so the door panel. So our clients basically say the design in front of the door panel, but now our CAD designers need to look to the other side, all of the clips that we need to all of the plastic parts to have a safety door panel. So this is a very important skill, the CAD design. We also have in the plant the painting and decor wrapping department. We also have electronic engineering, which is important because cars now have electronics everywhere. We also have physical prototyping in CMOLDS. We have additive manufacturing laboratory where we can have these physical prototypes to show to our clients what we are considering to produce and not waiting for the serial production to start. And then we also have a laboratory where we can do a lot of the validations needed for the automotive industry, which are a lot of specifications, requirements, and validations for chemical validations, endurance, climate validations, mechanical, electrical, and so on. CMOLDS Plastics is already certificated to do some of the validations, and we do this in-house. We also now are starting to have this lighting optics engineering department and skills, because now cars also, it's not only the lights outside of the car, but now inside we have a lot of lights, and this is starting to be a requirement from our clients. And because of these new, because of these new requirements from our clients to have light and electronics and displays everywhere in the car, it was important for CMOLDS Plastics to have a research and innovation department that is growing in the last 2 years. And this is based on 3 main needs that we need to, required to have to face the challenges of the future. Of course, the customer orientation, what our clients want, the evolution of the market and technology, we need to be in line with this evolution, and also, of course, the strategy of CMOLDS, the business strategy of the company and the technology plan. And this, of course, with the open mind for sustainability, competitiveness, and the knowledge required.
The research and innovation units, as well as our production plants, are spread among Europe. We have the headquarters in Portugal, but we are also present in France and Germany and Spain, where we will have our future technical center. To thrive on the automotive sector, we need to have a good innovation network around us. And that's why CMOLDS Plastics collaborates with a huge amount of research centers from the north and center of Portugal, namely CEIA, INEGI, INL, among others. And the same happened in France, where we work with several research centers and partners from around the country, and as well in Germany, Switzerland, and Austria. Starting to present the work developed by the lighting unit, and following our customers' needs and CMOLDS' will to start new business areas, we intend to manage in-house the design and the production of light guides, from door panels to dashboards to light central consoles. The benefits go from production autonomy, higher responsiveness to customer requirements, and great customization. To this end, we have been gathering new lighting skills in-house, like modeling with optical accuracy, using optimization and simulation tools, that give us accurate results and the ability to analyze and testing our prototypes.
Okay, so as we know, to have light, we need LEDs, we need electronics. So, and that's what this is what I do, and our colleague Luis, we develop this hardware. So we need the RGB LEDs and the RGB drivers, and I basically do the software for these drivers, for the microcontrollers, for the user to select the color that he wants in the car, or the effects of fading or dynamic lighting in the car.
So the innovation framework of CMOLDG go from energy storage, new technologies and materials, clean technologies, lightweight and sustainable programs, but also digital evolution, quality and comfort, and design and decoration. And these are the frameworks on the left that we will present here today. Starting with the digital evolution, Model Top was one of the first projects with lighting at CMOLDG Plastics. Here, the goal was to develop a complex architecture with 1.6 meter length, that is a huge plastic part, with light that is user-centered, allowing lighting synthesis for the light atmosphere inside of the car. As you can see, the developed part is a roof console that mimicates the light outside the vehicle, or mimics, sorry.
So I will present now the S console project that already ended in 2019. This was a big project from about 2020 between CMOLDG and Senti. So this intended to develop a new innovative central console for the cars of the future. And this integrates innovative functionalities within the console, and also the communication of electronic systems with sensing and illumination. So this has a lot of functionalities. I will show you some of them. So we have a magic touch display in here. Okay, we have a smart cup holder, and this is smart. Why? Because the cup holder can warm your beverage or cool down your beverage, depending if it is an iced tea or a tea. And you also have an inductive charger where you can put your phone to charge without any wires. We have a gear selector using only your finger, where you can put in driver mode or in parking mode. We also have a smart storage, which identifies what you are storing. So if you have your keys or your cell phone or your wallet. And we also have a flexible keyboard there on the side that is basically a textile that you push down and you have your keyboard there. Following this project that had a huge success, LAMSA projects arrives. This is lightweight electronics by injection molding in a seamless architecture. So this is a big project between CMOLDG, DTX, CEA, Celoplage, Min University, and Bosch. I am currently working on this project. This is also for a central console, but with a disruptive components for automotive interiors. So CMOLDG is working on the top part of this console, the transparent touch display and the touch display. Yes, that one. This is the Batman. We call it the Batman part because of the years. So we have there the touch display being built within the in-mold, and then we have three main technologies in this part. So the idea here is to have the electronics and the decoration and the plastic part using only one process. So while we are injecting the plastic, the plastic, we have in the mold, in one side, we have the ink transfer, the decoration part, so the in molding decoration. And in the other part of the mold, we have a foil. So it is basically the electronics. We have a flexible electronics with LEDs inside. So, and then the mold closed, we have the injection of the plastic, and we have that battlement part with already the decoration and the electronics. So this is just the video of the mock-up. So we have these parts, the storage also in there, and the armrest. This is the display. The interface is done by SEIA, and the capacitive foil is also inserted in the molding electronics. Then this part here with the capacitive buttons and with haptic feedback for the user to feel that the operation was done, is this piece is done by Celoplast. This is a back display. The displays are given by Bosch. And this we will have in the bottom a slider where we can change the volume of the music, the colors of the ambient lighting, and the intensity of the ambient lighting. And there a projection screen for the driver. Okay. Other smart interiors following this project, and also the door panel that is the core business of CMOLDS. There are two case studies, also one for a hidden until with center console with flexible displays, OLEDs, and also to have some haptic feedback in the console to integrate all of this. And another case study that is to have a dynamic lighting in the door trims with several LEDs, and also capacitive buttons backlighted.
Jumping to quality and comfort, we have the project called Substrate Sensing by Electronic Printing. With this project, we want to use a decorative digital printing process that allows functionalization, thus obtaining a touch surface in armrest part and the decorative backlighting effect in the insert area. The main goal is to produce prototypes and final demonstrators on the SEAT Ibiza door panel, front left. That is one of the serial projects that we have in-house for product and process pre-validation. Here, as you can see, we are testing several technologies for the backlighting effect, and one of them is using ultra-thin light guides, as you can see here in this picture. This film has no more than 2,000 micrometers thickness. Regarding design and decoration, CMOLDS had in the past a project using photoluminescent materials composed of particles able to store energy when exposed to light and then to emit that light when set in dark conditions. Using inorganic components, one particle type per color. These materials were used in a pre-series production for the Opel Grandland X, and the materials were used here in the armrest part. The shape is like a normal light guide, but it's a passive part because we do not have any electronics, nothing, and on the dark we can see it glowing. One of the biggest projects that are currently ongoing in CMOLDS is the future door panel. With this project, CMOLDS want to develop new solutions and processes for the reduction of door panel weight and decrease of assembly time. To this end, we developed a modular architecture and disruptive design of the door panel, allowing product customization. This means that we will be able to assemble the door panel from the front, and we can change For example, this part without changing that one. If we have a problem with the upper area, we can change it without having to change all of the door panel. And this will give us a huge flexibility in when we will have to assemble the door panels. We also want to develop coatings with thermal management properties to maximize driver comfort. This means that there will be areas in the door panel that will be heated, and the driver will feel the comfort of having the door handle and the place to put the harm cold or heated. We also develop new acoustic solutions, miniaturized, allowing more space for other functions, and new light concepts such as backlighting, illuminated sewing, and LEDs matrices, creating different ambience moods and deliver warning information notes to the driver. And we want to replace the traditional mechanical buttons with touch detection and haptic feedback functionalities, which means that in this area we will not have physical buttons, but haptic effect when we'll try to open or close the glasses. Here you can see a video of the door panel and all of the areas where we are currently working and trying to innovate in one of them. In the door panel insert backlighting project, this is a higher TRL project. We intend to make prototypes for door panels inserts with backlighting based also again on the SEAT Visa door panel for product and process pre-validation. Here, what we are using is a sheet of optical fibers connected in one of the edges with an LED, and the optical fibers have a texture on the surface, allowing the light to be coupled, and we can see the light in the perpendicular direction of light propagation inside the optical fibers. This allows us to assemble the optical fibers with finalizing materials, STPO, PVC, or 3D fabrics, and allow us to have this effect, or when the lights are off, we cannot see anything, but when the lights are on, we can see the pattern that we put on the material or the perforation that we do as well on the material. These are some of the photos of the inserts that we developed, and as you can see here, we are able to have different lighting effects using the same technology. This project was already shown to SEAT, and we are trying to validate it for the next projects with them. So this was our presentation, and the presentation of the topics that seemed to us related to the topic of this afternoon meeting. And we would like, first of all, we would like to thank you again, the organizing committee, but we also have to take a note to thank our colleagues at CIMOLD that have been developing all these projects, not only with us, but also with us. Thank you.
Thank you.
Okay. Thank you, Rita and Anna Rita. I don't know if there is some questions or comments. Yes.
I don't know if you can answer that.
eventually.
But as researchers, we always try to answer the challenge. So I would like you to speak what you can about the recent challenge that you've been facing in your work. Not the personal life, just
Technical ways are a lot. So one thing that I can say, I'm not there to less than a year. One of the concerns of the company like this in the industry, in the automotive, where are we talking about clients and so on, is money. Money runs everything in this industry, in this and others. So this is a challenge for everything. Everything that we do, we need to think about money that will cost. Of course, as we are in the R&D, we also look for the innovations, right, to see what people want in the car.
Exactly.
Looking already for automotive driving, the buttons that we need for automotive driving, and not for the car that we drive.
Exactly. And our position in the company nowadays is we are mainly our work is to try to solve problems that OEMs cannot solve.
Yes.
So they come to CMOLD and ask for some crazy idea that their designers thought and tell us. So we have this idea, try to put it in a demonstrator. It cannot cost more than €2 per part or something like that, and we our goal is to have solutions for their problem and exactly. So our everyday issue or is money and to be able
to engineering
exactly
because
to think ahead. Yeah, exactly.
The designers
We need
to
to be ahead of their problems, because when they come to us, we have to have the salvation
with the lower cost.
exactly. And for yesterday.
Okay, so I think that it's time to finish now. So I'd like to acknowledge again Ruth and also especially our guests Vânia Freitas, Ana Rita Frias, and Ana Rita Barros. So thank you so much for accepting the invitation to come once more to the university and to share with us a reality which is different than the one that we are embedded here. Okay, and then Lionel and the other people that are online. So thank you so much for your participation, and we will come back next week with a section, I guess, in Brazil, in UNES. Okay.